I'm Professor Lucy Rogers, the inventor with a sense of fun. And I've made it my mission to travel the UK to discover how people and places are using everyday tech to give themselves the engineering edge. I've just arrived at the Surrey Space Centre, which is one of the world leaders in the research and development of low-cost technologies and applications for the space industry. I'm really excited because I have heard that they are using laser systems that will be used to make more accurate atomic clocks for use in space. Current clocks, such as those in Galileo, use microwaves and tend to be quite big, and they're expensive. These clocks are also quite sensitive to environmental conditions, so heat or magnetism or radiation. Therefore, their own environment has to be kept stable, which is a problem in space. The next generation of atomic clocks are going to use lasers instead of microwaves. And here at Surrey Space Centre, they're using everyday technology to actually make laser systems for use in space. I really can't get my head around how this is going to be everyday tech when, to me, that should be just something that's in a laboratory. So my big question is, how can everyday tech give a laser atomic clock the engineering edge? Today I'm at Surrey Space Centre and I have just been brought into the most exciting room. Chris, where are we?
Hi, so I'm Chris Bridges and I'm an academic here at Surrey Space Centre. So we're in our ground station here, and you can actually see around you the racks of radios and computers that we use to then transmit to and from our spacecraft.
So we're actually in the room that's talking to spacecraft.
Yeah. And all the computers you can see here are all of our command interfaces that are used to then speak up to either satellites we've built, satellites we're working closely with our partners, or some of our training exercises. So we use this room not just for running our real missions, but actually for teaching.
Wonderful. So from here, we can control some satellites, we can get their images down, we can actually see what's happening.
Exactly.
And train new people how to do that, so when they've got their satellite going up,
exactly,
they can control it themselves.
Yeah, we're quite fortunate. We've been running a long time, and so we do help out a lot of other institutions that are doing this for the first time. So here at Surrey, we're quite famous for our small satellites and our small satellite work, and all of the things you can see kind of around you is just kind of a testament to how much time, effort and energy and people have kind of put into these kind of facilities.
Yeah, and it's really quite sci-fi in here. We've got a load of huge, big, flat screens, a load of very comfortable-looking chairs, and racks, server racks. They must be 8 foot tall, 4 foot wide, all very space age black. I think you must choose just black equipment specifically.
We have. The only thing that this room is missing that I'm working on is the Jean-Luc Picard captain's chair. Yeah. Which I feel is mandatory. We've got the blue neon lighting, as you can see around the edges.
Of course, yes.
In case we need to go on red alert as well.
I know satellites have an awful lot of sensors, electronics, components inside them, but I don't really know the challenges that are facing some of these satellites or some of the engineers and scientists who are actually doing work with and on the satellites. So I'm now going to speak to someone who can tell me a little bit more.
Hi, my name's Peter Nisbet-Jones, and I'm a physicist working with the guys here at Surrey Space Centre. I'm trying to build quantum and atomic sensors and laser instruments which are small enough and robust enough to put in spacecraft.
Okay, so quantum and atomic, this sounds really scientific. And to get them up into space, so I'm imagining that most atomic clocks are really rather large at the moment.
Yeah, at the moment, most atomic physics experiments are experiments. They're in physics labs, in research universities and institutes, and they break if somebody sneezes next to them. And this isn't really good enough if you want to shove something on a rocket and shake it about a bit and throw it into orbit. So there's a lot of engineering which needs to be done to take these experiments and these sensors and things that other scientists are developing across the world and make them small enough and robust enough to be able to be sent into space.
But there must be some atomic clocks in space already.
Yes, there are a lot. That's how GPS works. GPS is just a network of atomic clocks floating around in orbit. But they are based on microwaves and existing technologies. And the next generation of atomic and quantum sensors and clocks and instruments are thousands of times better. But they're still stuck on the ground in Earth. And if you tried to put one in orbit, it would break instantly.
So if you actually got a more accurate atomic clock up into space in the GPS system, we must be down to meters, I suppose, that it can tell us at the moment. And that's with the microwave atomic clocks.
Yep.
But with lasers, what are we going to get?
The best laser clocks are probably about 5 orders of magnitude better than what is currently in space. So you can imagine 1 million times improvement.
So I'm just trying to work out that's, it'll be able to tell if it's on your middle finger or the index finger, or better.
If you had the very best atomic clock in space, you could use it as a GPS around the outer reaches of the solar system, not just on planet Earth.
Okay, so one of the reasons why you're looking at putting these more accurate atomic clocks into space is not just for us here on Earth, but also going out into the solar system.
Yeah, there are loads of things you can do. You can use them for navigation around the distant solar system, but they're also incredibly precise sensors of fundamental physics. So they're really good instruments for looking at how quantum mechanics and general relativity are connected, and all sorts of quantum sensors, extremely precise magnetic field sensors, gravitational field sensors. There's loads of things you can do with quantum and atomic sensors.
So the atomic clocks we've got at the moment using microwaves are good enough for various things. But to get that extra accuracy using a laser atomic clock, at the moment only these laser atomic clocks are in physics laboratories and have to be really specially controlled.
Exactly. They're currently just too delicate to be used anywhere other than an extremely expensive lab.
And scale?
A typical lab at the moment will have 2-3 tons of equipment with kilowatts of power, with a temperature stabilized room to fractions of a degree, with foundations which are drilled into the bedrock. They aren't something you could ever move or take anywhere or do anything with.
So what you're actually trying to do is to make the laser atomic clock available for many physicists around the world to do other experiments. So it'll just be, we haven't got to do an experiment to make the laser atomic clock. We've got a laser atomic clock. What experiments can we do with that?
Exactly. We're trying to do the engineering for the physicists so that they can do the physics themselves.
I still can't quite get my head round how everyday technology can give these physicists, these engineers, an engineering edge to actually make laser atomic clocks with the accuracy that can, at the moment, only be achieved in a laboratory. I think I now need to go and see if I can find one of these things on the workbench. I'm in one of the research labs, and it's got the feel of a bit of a clean room, but there's also electronics workstations. I can see oscilloscopes, soldering irons, multimeters. There's a huge 75-inch monitor just sitting on one of the workbenches, and all sorts of bits of very shiny metal that looks like they're being put together in a very precision manner. There are all forms of measuring device as well. It's a really quite an exciting lab.
So what we're looking at here is, I guess, our elegant breadboard system of our first stabilized laser.
It's much, much smaller than I was expecting. It's about the size of 2 computer keyboards.
Yeah, about that size. Yeah, well, we've essentially got inside here just a piece of metal base plate, but then it's essentially 2 key parts. One is the actual laser and the opto-electronic side of it itself, and then we have then the digital side, which is then a fast FPGA and a very fast temperature controller.
And FPGA, field programmable gate array.
That's right.
Can you explain that a little bit more detail?
So a field programmable gate array is essentially a blank chip. You essentially have a number of logic cells in it that contains things like truth tables, registers, NAND gates, this sort of thing. But a user can just go and program them, so it has these very small micro switches in them. And that's really important because we need this thing to operate very, very fast. We're, rather than sort of making a bespoke chip, going out and building it, waiting for it to come in, we can use these to do some very quick prototyping.
And they're just off-the-shelf
Absolutely.
component.
Yeah. We go out and buy all of our electronics straight from commercial off-the-shelf.
Like RS.
Yeah, so this is essentially just a very, very fast controller that is just focusing on making the laser stable. If you kind of leave it on its own as the thing kind of warms up, it will just start wobbling about, the bandwidth will change, and the actual finding this point where you're using as a reference keeps moving about.
Yeah.
But in our case here, what we're using is then some conversions, either going from the optical world to the digital world to then make that into a fast control loop. And of course, we much prefer doing that in digital with noughts and ones that we can play with ourselves.
So what we've got in here, I can see the laser, but that's just a normal commercial laser, yeah?
Yeah, that's right.
What sort of thing would that be used in?
So we would use those types of lasers usually in telecoms industries. So it would be the sort of thing you'd find like outside in the road for connecting your Virgin Media, your fibre.
In those green boxes by the road?
Yeah.
Okay.
All of those sorts of lasers are used in those sort of applications that pushes the internet around.
Right, so they have a reliability and an accuracy, but it's not going to be good enough.
Exactly. So
Right.
it kind of goes half of the way there because obviously they're designed to work, really cold. They're
Yeah.
designed to get really hot. So they've already had a lot of the kind of environmental rigor that we need, certainly for the applications in space that I look at.
So that laser is going through some fiber optics and actually exciting a gas here.
Yeah, so here we have an acetylene cell. So what actually happens is the laser is essentially being scanned. We are actually changing it digitally to scan across really what this atom's response and reaction is.
Yeah.
And what we do is we find that when it reacts at a certain frequency or wavelength, depending on your style of physics or engineering, you can then actually use that as a reference. And so that's what we are then stabilizing them with digitally. So that's what the FPGA does.
And so you're taking that trigger of, when that frequency has been hit, and you're feeding that back in?
Yes, so this is what this photodiode does. So
Okay.
we can then actually go back from the world of opto into digital electronics and, either analog voltage or digital noughts and ones.
So the photo is going to be, this photo sensor is analog, so that have to go through an analog to digital converter?
Yep, so that's really what goes into our FPGA here.
All right, and so the FPGA does the maths and sends back out a digital signal,
Yes,
which then feeds back into the laser
correct.
to go around again. And so that laser is more stabilized each time it goes around the circuit?
Exactly. So we do that loop as many times as we can. And what the 2 triggers that we're looking at here is one is controlling the temperature. The other thing is then controlling the current. And we kind of use both of those 2 to then manage how the laser moves around with respect to this response from the acetylene cell.
So is anything in here bespoke?
The PCB board is bespoke. We've built that. There are small sort of digital electronic boards that are bespoke. And in our project, what we'll be doing is then bringing a lot of this stuff down even smaller. So we need to integrate this now much, much more to make it something a lot more precision.
But the components themselves are
absolutely.
all off the shelf. So
All of
it's
it.
really just the effectively the wiring of the circuits
Correct.
that you're doing is the bespoke bit.
Yeah.
So I can see this is much smaller, and if you're using commercial parts, it must be cheaper.
Yeah. So if you were to build something typically in the lab with the usual mirrors, you still need the laser, you still need digital circuits. You're probably looking anywhere from just 50k just in those parts. You're then going to have to spend time and effort in labor into then refining the system to get it to a point where it can then do your science, as well as then having an actual facility to do it in. So you can easily double that to 100k, whereas this one here, the prototype that we have now, is probably around 10.
Wow. And once the lid's closed, you just press go.
Exactly. It's a stabilized laser that you can then do your physics with.
Wow.
And that, in our case, we're looking at then laser ranging, but there are atomic clocks, there's quantum stuff, there's laser communications, there's all sorts of things that come on top of that. But the core technology of having a decent stabilized laser is the common denominator in so much of what we're going to need in the future.
I can see the advantages of physicists being able to have this, but to take it up into space must have a lot more challenges.
Yes. So there are a couple of things that are vastly different here on Earth. Everything's quite nicely temperature controlled where we can. In space, depending on what orbit you go to, and we're hoping for stuff, certainly interplanetary, you're looking at very, very cold temperatures. So things that can go down to easily minus 200 or even plus 200, depending on where it's got to go.
200 watts.
Degrees C.
Right,
okay.
C, yeah.
So that's one part. The next part is then the actual radiation environment of operating in space. So that kind of comes in two main streams. One is what we call single event upsets, which are particles flying through your equipment, and that can cause noughts to ones, ones to noughts, and maybe even burn out electronics. And the other one is called ionizing radiation, okay, so total ionizing dose. And that is like a constant trickle that eventually change then the actual physical makeup then of your electronics and your silicon.
And how are you going to get this ready for space?
So what we need to do to this particular unit is we need to start adding sensors. We need to start adding redundancy to the system. So things that where we have like a critical resistor that's being used that we know has to be precise, well, we can use multiple different versions of those. We then take lots of instrumentation measures so that if we know the system drifts around, well, actually, we can use that to our benefit eventually. So long as you know what the system is doing when you're in space, you can then try and figure out then what is physically happening. The important bit here is that this is then going to be put into an object that's going tens of thousands of miles an hour up in space. And so we need kind of almost like multimeters or small pieces then that you can attach to all the critical points. So collecting what we call the data and the telemetry off the instrument here is the piece.
And I'm still trying to get my head around that it's just an FPGA. It's just it's a photosensor, laser. It's stuff that some of this stuff I've got in my own lab at home.
Yeah, exactly. This is all just everyday technology that you have in your home, use for your internet, and being used to prototype things in labs, all around the planet.
So not only is these lasers going to be used by scientists, eventually that will trickle down to positively affect our worlds.
Absolutely. So everyone wants, that faster and better, internet connection out to their homes. It will do that, but it will lead to then more precise GPS. It will lead to better and newer instrumentations for climate monitoring. It all starts with these key pieces of technology.
I'm back in the ground station and looking at the picture of the Earth and the satellites going across and seeing how many satellites there are. And this is just a small selection of what's actually up in space. The technology that's in the satellites that's going to help the atomic clocks is laser technology. And in fact, most quantum technologies are actually using lasers. So what Peter and Chris here are developing is going to affect many, many things, not just up in space, but also down here on Earth. And to me, it's been great that Peter, who was working in a physics laboratory, saw that there was this need, and he actually knew that it could be done another way. And so he's gone out of his way to actually make something that he wanted for himself. When he was a physicist in the lab, he wanted it. And working with Surrey Space Centre and working with Chris, he's gone to make it. Every spacecraft and satellite that's up in space at the moment that's using a laser is using analog technology. And most of this has been built in a bespoke manner specifically for those spacecraft. What the team here are doing, they're using digital signal processing, the same stuff that is used in mobile phone systems and fibre broadband, and that everyday technology is giving them the engineering edge.
I'm not sure about atomic clocks, but my internal clock tells me that it's ice cream time. You coming?
You've been listening to The Engineering Edge with Professor Lucy Rogers, with thanks to Chris Bridges, Peter Nisbet-Jones and the Surrey Space Centre. The producer was Becky Singh, the series editor was Dan Page, and it was a Why Did the Chicken production for DesignSpark. If you enjoyed the show, then please do 3 nice things for us. Subscribe, rate us on iTunes, and tell a friend that this is the best podcast you've heard since the last really good one. For more episodes and bonus content, head to designspark.com/podcasts.
Ice creams.